Hello, this is Oğuz ARDIL. In this video, I will show my LE419 integrated circuit course class term project. My project was to design an 8-bit Siso type shift register, and I have used a basic design from Geeks for Geeks as shown here. The only difference is that this design is for 4-bit shift register, so I had to combine two of them to reach the final 8-bit shift register design. And in my design, I've used negative edge triggered D flip-flops, and I've connected them serially, and I've used the better spice coding to all of that to eliminate the clock race condition. Because in digital circuits like this, it's a strong concept to be eliminated to have in order to have a better output. So in my D flip-flop, I've used the two combined D latches, which is a basic schematic of D latch is shown here. And this is from our course slides. The D latches, I've combined them together, and the only difference is that in our clock cycle, first D latch gets the positive clock cycle in the transmission gate PMOS side, and for the other D latch, the clock cycle gets reversed to have a negative edge triggered D flip-flop. So here's our electric VLSI D latch schematic here, as shown here, and which is a basic design, nothing too shabby, just a normal design as I show. And here's the layout. And in my layouts, I've used the TSMC 180 nanometer technology and 3-layered metals. And last but not least, lambda set to 90 nanometer scale, the MOCMOS size, because after a bit research, a lot of research, I saw that in the internet, all the sources are stating that in the TSMC 180 nanometer technology, we have to set the lambda for 90 nanometer for better optimization. So here's my D-latch design. Try to minimize the layout design. And here's my D flip-flop schematic here. And I just combined two D latches together and one inverter to reverse the clock cycle. And here's my D flip-flop design. Nothing too shabby, same inverter here at the start, and one D latch, another D latch, reverse clock cycle. And here is my final 8-bit Siso type shift register schematic here. And I just combined 8 D flip-flops together. And here's my final layout. In my layout, I tried to use a rectangular shaped design to have a better area management, and I've set my transistor sizes to a 2-to-1 ratio, 2 for PMOS, 1 for NMOS, and for the PMOS type transistor, I've used 10 for width and 5 for length, and for the NMOS type transistor, I've used 5 for width, 5 for length. And in my spice code, it's just the basic spice code. Here's the DC value for 0 to 5. I've set the high value for 5. Here's my input pulse, 200 nanoseconds per period and 100 nanoseconds at the peak time. And here's my clock pulse, again, 0 to 5, 20 nanosecond period and 10 nanoseconds peak time, and transient set to 300 nanoseconds. And here's my final output at the LT spice. We see here the clock cycle. We can track the clock cycle in the first negative edge. We can see that our input is 1, so our output Q1 is getting set 1 here, and in the here is the last negative edge. We can see that it gets 0 here. And for the main idea of the shift register, we have to shift 1 bit at a time at the output. So every clock cycle output will be shifted 1 to the right. So here's in the next negative edge, we shifted the Q2, and the third negative edge, we shifted the Q3 here, and the fourth, and so on and so forth here. So if we track our output here, we can see that in this negative edge, we can track it here. So first negative edge here, second negative edge, third, fourth, fifth, sixth, seventh, and eighth negative edge. You can track that, and serial output is in the 8th negative edge clock cycle. So our output is shifted 8 bits to the right, and the circuit is working fine. Thank you for watching.